Hey folks, good morning, or whatever time it is wherever you are. Uh, Today I'm going to show you the Tangled game. So when I did my first episode, I committed the cardinal sin of assuming that everybody knows what the hell I'm talking about with this particular game, which obviously you don't, because this game doesn't actually really exist. It's just something I made up. Um, I've written quite a bit about it on the blog, so I'll put some links to those posts in the show notes. Um, but I figured it might be useful to just actually go over what the game uh, consists of and how you play it and all of that. So what I'm going to do is just going to bring up a visualization I created of the game. So just hold on a second here. So this is just I'll just let me show you what's going on here so that you know what all this what this junk is. So the game is a game, so you can win and lose. You can create a leaderboard. So this is just a tiny leaderboard that I made up for this particular run through. And there's different kinds of players. So you can create agents that are different types of AIs that learn to play a game like this, and or you can play it as yourself. So this is just a little leaderboard. This is just a fun graphic. There's two players, player one and player two. So you can choose which agent you want to play the game. So for this run through, I'll play both sides. So I'll be player one and I'll be player two. So once you select the players, the two players then get highlighted up here. The current player has their box outlined with whatever color they are. So red goes first in Tangled. So the red me is the first player. Okay, so Tangled has, no matter what graph you're playing on, by the way, back up a step, a graph is a set of vertices and edges. Vertex are these round circular things, and you can just think of them as like dots or circles. There's some thing that you want to, well, let's just consider it to be an abstract mathematical object now, like a graph. They can represent things in the real world, but right now it's just a bunch of dots. Those are the vertices. And these things that connect some but not all of them are called edges. So when I say some but not all, you can see that 0 and 2 are actually not connected directly by one of these edges. And the collection of vertices and edges defines a graph. So this is a particular graph. This is the one that I call the ridiculously small graph in the blog posts. The ridiculously small graph is really ridiculously small. There's only and I should mention also that just in terms of terminology, this is what's called a connected graph. So what that means is that there's no vertices that are hanging off by themselves with no edges connected to them. So for reasons entangled, disconnected graphs are not all that interesting. So when you play, you're always playing it on a connected graph. So this is the second smallest connected graph there is. The smallest connected graph is one where there are only two vertices, say this one and this one, connected by one edge. And the reason I'm not using that one as a demo here is that they always end in draws. So that particular graph is too small to have a winner for this game. So this is the smallest one where you can actually have a winner. All right, so it's red's turn to go first. They face this open board. And in Tangled, there are two types of moves that you can make. You can either select one of the vertices, but you only get to do that once a game. So that would be coloring it your color. See, they highlight red. So if I were to select one of them, I would permanently own it, by which I mean it would turn my color, in this case red. And the other thing you can do is you can select an edge and color it one of three colors. So the red goes first. Now we have to make a decision as to what we're going to do. So what I'm going to do is I'm going to color this edge. No reasons given yet. I'll just show you. And the three colors I can color it are gray, green, or purple. And I'll explain in a minute what those colors actually represent in the game. But let's say I was to color this one green. So I was red and I just made a decision. And the way I actually physically did that is I used my mouse to left click on the edge. So I'm just given an input and selected and turned the edge green. Now it's Blue Me's turn. So now Blue Me has these Blue Me. That's funny. Sorry, I'm really just a 13-year-old boy in a 70-year-old man's body. They have the same set of choices. They can color one of the vertices their own color, which is now blue, or they can select an edge. But when I cursor over the edge, you can see nothing happens, and there's a reason for this. Tangled has one extra rule, so it's pretty simple. You either color an edge or you select your vertex. But if there's exactly one edge that hasn't been colored yet, you have to pick a vertex. So the reasons for this is that if you don't have that particular rule, the game can get into a state where you can't make a legal move. So in this case, we've triggered that particular thing. There's only one unselected edge, so now we have to pick one of these three things. So let's say I pick this one. So I'm just going to select this vertex here. So now that belongs to the blue version. Now it's red's turn again. We're just alternating turns. And again, this red player is now faced with the same scenario that they can't select an edge because there's exactly one unselected edge and they haven't played their token yet. So they have to pick one of these two positions. So let's say I pick this one. Now it's blue's turn, and blue has three choices now for this edge. They can color it gray, green, or purple. And what I'm going to do is I'm just going to color this one purple. Now, let's forget about all of the stuff that just showed up on the screen for a minute. The game is over when all of the edges have been colored in the graph and both players have played their position, their token. So the full gameplay is really quite simple. You just alternate turns, coloring an edge in a graph or selecting your token, which remember you can only do once. And at the end of the game, when all of the edges have been colored and both tokens have been played, we're in what's called the terminal state in the game, which is the end of the game. And once the terminal state is reached, then the game is adjudicated, which means the winner is determined. So the gameplay itself is really simple. Like this, it's not hard to understand the moves that you could make, but the difficult part of this game by design, so this is a type of game which is designed to have this feature that I'm about to describe, is that computing who won is a mathematically difficult problem. So it's a problem for which conventional computers don't deal with well as the problem gets bigger. So for small things like this, you can just brute force it and you can get the exact answer to the problem and everything is fine. But as the graph gets bigger, the problem explodes in difficulty to the extent where conventional computers struggle and then ultimately fail. But there's a chance that quantum computers can do this type of problem more effectively and therefore can provide solutions to the who won question more effectively, potentially. So what are these numbers about, and what are we actually doing when we compute the score, and how do you kind of intuit how to play this game well? So the game is won by the vertex, so there's only two that matter, the one that red picked or the one that blue picked, that has more of a quantity which I'm calling influence. So the influence of a vertex counts the correlations between that vertex and so let me back up a step. Again, I'm doing this thing where I kind of assume things that are not at all obvious, and I think um, this would be helpful to have some more graphics, but I don't have them up yet. So let me try to just describe this in words. So the imagine that each of these vertices has kind of like a hidden little magnet associated with it. And the magnet can only be in two possible states. One is its north pole is facing up, and the other is its north pole is facing down. So let's flip our perspective a bit and think about each of these vertices as now being a little magnet that has this hidden arrow that either points up or down. So the hidden arrow is going to be the same thing as the state of the vertex. So imagine at the end of the game, we're going to try to figure out whether these arrows are pointing up or down for each of these vertices. So how do we do that? What the colors of the edges represent are coupling strengths between different pairs of these little magnets. So if you've got a green line, what that means is the magnets want to be aligned alike. So if you look at the line between 0 and 1, the green line represents the desire for 0 and 1 to always have the same direction. Now they could both be up or they could both be pointing down, but they're preferentially locked. So in the study of magnets, this is called a ferromagnetic interaction, which means if you have two little magnets, they want to point in the same direction. So north pole up, north pole up, north pole down, north pole down. Purple is the opposite thing, where purple means you want the magnets want to be aligned in opposite directions. So if one is pointing up, two is pointing down. If one is pointing down, two is pointing up. So those are the energetically preferred solutions. So now if we look at the combination of these two in this graph, if 0 is up, 1 wants to be up, and 2 wants to be down. So we get up, up, down. 0 and 1 want to be in the same direction, and 2 wants to be in the opposite direction. And if 0 is down, then 1 wants to be down, and 2 wants to be up. So there's two equivalent possibilities here, both of which satisfy all of the constraints of the graph: up, up, down, and down, down, up. And just by the way, all of the kinds of things that occur in this particular type of problem, this tangled problem, all have this feature that there's always a twofold degeneracy in the ground states of the system, because you can always reverse all of the spins and you get this, or the magnet directions, and still get the same energy. And the reason for this is that, again, this is a little bit technical, but for those of you who know a little bit about magnetism, there's no bias on any of the magnets, which means neither of the magnets has an energetically favored direction. It's all the same to them if they're pointing up or down. There's no bias at all on any of them. They're only coupling terms. So now that we kind of know that the energetically favored states of this thing are down, down, up, and up, up, down, we can now ask the question, how correlated are the states of 0 with the states of 1 and 2? Let's say we'll ask that question. Well, this one is always the same as this one, regardless, like it's either both down or both up, and it's always different than this one, so it's always opposite. And the reason why this one is always opposite to this one is that this one and this one are the same, and this one are opposite. So if these two are locked together, then this one is always opposite for that one. So down, down, up means the first down is different than the last up. So this number here, -1, which is associated with the vertex 0, is the sum over all of the, it's the correlation between this vertex and blue. So wherever the blue tip vertex is, you write out a number, correlation is -1. This one is also anti-correlated with 2, so you get this -1. Now if we ask the same question about the correlations with red of these two, this guy is anti-correlated with red, so they're opposite. So this one is fully correlated with this one, so it's +1. Now the way that the game is scored, I know that this is tedious, bear with me. It actually, it's a lot easier to explain this in math than it is in words, but bear with me. These purple numbers, which are kind of the point of it all, which are these numbers that I'm calling influence, is the sum of the correlations with all of the vertices that are not the one that's being singled out. So for example, 0, I'm going to count all of the correlations with every single other vertex in the graph, and in this case there are only 2, and then I'm going to add them up, and that's going to be my purple number. So this guy is +1 correlated with this guy, so the purple would be +1 if that was all there was, but it's -1 with this guy, so +1 -1 is 0. This guy is +1 this way, -1 this way, which is 0. But this guy is -1 -1. So it gets a score of -2. So let me just say this again. So every single vertex in this graph, you can ask, how correlated am I with all of the other vertices in the graph? And then I add up all of those numbers, and that's the influence score. That's that purple thing that I'm showing. And at the end of the game, what we do is we ask for the specific vertices that red and blue have taken, who has more influence. And whoever has more influence wins the game. So you can think of it like if I'm let's use a voting analogy. So let's say I'm electing a leader, and I'm an influencer, or at least I think I am, and there's another influencer out there, and we're going to play this game where if I say vote for candidate A, and you say something else, how many of the people around me are just going to vote for candidate A just because I said so? Because I could then ask the question, well, if I said vote for candidate B, would all of those people follow me as well? So that's why I'm kind of calling this influence, is that it doesn't matter which way you vote in this game. What matters is how many of the rest of the people, or the magnets or the spins, follow me or are correlated with me regardless of the direction that I pick. So if I'm up or down for 0, it doesn't matter the influence is the same number. And in this case, red wins because 0 is bigger than -2. So blue here, everybody always disagrees with him no matter what he says. So if he says, yeah, we should go up, these are both, no, we're both going to go down. If he says, nah, we should go down, then these are both like, no, we're going to go up. So no matter what happens here in the end of the game, 2 is always disagreed with by everybody. So he's got a bad negative score. And that's not a good place to place your vertex. And that's what blue did, and that's why they lost the game. Okay, so what I'm going to do now is I'm going to run the same type of thing. So we're going to play Tangled, but we're going to do it on a bigger graph this time. So just give me a second while I load it up here. Okay, so it's the same setup. What we're going to do is I'll play red, and we'll have one of our AI agents, let's say the random guy, play blue. So here we got a bigger graph than before. This is called the Peterson graph. It's got 10 vertices and 15 edges. So it's still very small as graphs go, but it is much bigger than the ridiculously small graph. And again, the Tangled is a pretty simple game in terms of what actions you can take. I start, I'm red. I can color any of the edges, any of the three colors, gray, green, or purple, or I could pick a vertex. So I'm gonna color this one green here because why not? And Random Randy, my opponent, picked a random action which was coloring this one green. So I've got a plan in mind here that, depending on how he moves, may or may not work. So what I'm going to do is I'm going to color this one green, and the reason is I'm going to try to make a big clump of green stuff. So you see now there's all these are connected with greens. Remember, green wants the system to like lock together. So in all things being equal, at least at this point in the game, all of these four vertices would all vote together. And he played here, which is to just zero coupling between these two. So I'm gonna grow this clump a little bit more, but I have to be careful because I don't want him to sit on it. So actually, you know what I'm going to do is I'm going to play my red token because I'm going to try to own this clump. So I'm gonna play red here. We'll see if that ends up working out, but I'm gonna play. And so he played his blue token on the fourth vertex, which is good for me because here's what I'm going to do. I'm going to color this one purple, and I'm going to show you, I'll tell you why. So if all of these guys are all the same, and I put a purple one here, that means that they'd want to be different than what 4 is, so they're going to vote differently than 4. So the situation I've set up now is that this clump of 3, 9, 8, 2 is all going to vote together and against 4. And what I'm going to do now is I'm going to cut 4 off from the world by coloring this guy gray. So when I do that, now 4's only interaction with the world is through this link. And so if I can make the thing that it's connected to always want to be in the same direction, and it'll be opposite 4, and I'm going to do great because I'm sitting on this clump. So I'm going to try to grow the size of this clump by coloring this one green. And he did this useless move up here, and I'm going to continue my exercise of making the clump bigger and bigger. And he just actually helped me there with that move because now 0 is part of the clump. I'll try to grow the clump a little bit more. So the move of making 3 and 1 opposite, so this is where you have to start thinking a little bit about what the right move to make is. So imagine this entire clump is voting up. This means that 1 is going to want to be down. So if I want 7 to want to be up, then I don't need to color this purple. Does that make sense? So up, down, up if these two links are purple. So I'm going to do that. And then after the game is done, the answer is adjudicated. And this is using simulated annealing backend to adjudicate the system. So simulated annealing is not exactly going to give you the answer that the quantum computer will. But for small graphs, I've tested that it's good enough. So what small graph means is a little bit smaller than this, and good enough means that it gets the right answer all the time. For this particular graph, I'm not sure it does because in order to test, you need to enumerate all of the terminal states and then check to see if the simulated annealing solution is the same as the quantum annealing one, which I haven't done because there's a lot of them in this case. The number of terminal states grows like 3 to the number of edges. And the number of edges here is 15, so 3 to the 15 isn't a ginormous number, but it's fairly big. And like I showed before, these numbers give you each of the vertexes correlation with the blue vertex. So for example, if you look at vertex 7, this top number here is the correlation of vertex 7 with vertex 4.
And it's hard to see directly why that number is what it is, which is part of the reason why this is hard for people. But 4 and 7 are connected, but they're connected through a very indirect chain. So 7 is connected to 6, is connected to 5, is connected to 9, is connected to 8, which is connected to 2, which is connected to 4. So all of these vertices share some connection with each other, which is why this ends up being a difficult problem at the end of the day. But the system's small enough to actually be able to evaluate what the number is. So the correlation of 7 and 4 is minus 0.778 or 6. And the red number is the correlation of each of these vertices with the vertex that red picked. So this one and this one are very highly correlated. And then the blue numbers or the purple numbers are the influence numbers. So those are the ones that matter at the end of the day. Now, if you look at the influence of 4, see it's huge and negative. That was by design. We basically created a situation where we were trying to pile on 4 to make sure that all of the other guys are going to vote against him. And the actually 1 is even worse for some reason. I'll have to check to see why that is. It could have something to do with these 0 couplers, but I'm not sure. And then the ones that are the most positive are the ones that are in the clump. So the 8 is amongst the most positive ones. It could be that these variants of these numbers actually comes from the not doing enough samples on the simulated annealing side. So this is an approximate solution. And as you draw more samples in the simulated annealing thing, you get closer and closer to the correct statistics. All of which is an aside. All I wanted to do is show you how the gameplay worked for this particular type of graph. Okay, so that was an introduction to Tangled. You can play it on any graph at all. The problem gets harder and harder to adjudicate as the graph gets bigger, depending on the tactics you use. And ultimately, what you want to do is send the final problem to a quantum computer, and specifically the D-wave type, because this problem that we're setting up on this graph is the exact problem by design. So we designed this game so that it had this feature that the D-Wave folks have claimed quantum supremacy on. So even though I've described this in terms of graphs and edges and colorings and things, the actual underlying machinery of how you compute the influence of all of these states is the problem that D-Wave has claimed quantum supremacy on. And influence has another name in the condensed matter community. It's called the spin-spin correlation function. So the spin-spin correlation function is a property of magnets, classical and quantum, and the D-Wave folks claim to be able to compute that quantity with supremacy. And I believe it. I believe the claim because the system itself, the D-Wave hardware, is essentially an analog quantum magnet. So it was designed, I know because I did it. Or at least I was in charge of the effort. That's supposed to be like a collection of little magnets that you can tune the couplings of, like I showed you today. Okay, I hope that was a clear adjacent or clear enough. And you'll be seeing more of Tangled shortly as we get closer to being able to actually do it on a big enough graph so that you can use a quantum computer to train one of these alpha 0 agents, and I'll touch on that in a future post. Okay, thanks friends.